Good morning, students. Today we would like to discuss electric current, conduction, and displacement current density topics. First, we would like to start with electric current. Electric current is defined as the rate of flow of net charge through the conductor with respect to time. The direction of current is conventionally in the direction of flow of positive charge. It is the flow of charge per unit time. If Q current is flowing through any cross-sectional area of conductor in time t, then the electric current I equal to Q by T. The SI unit of charge is Coulomb. Coulomb is denoted as capital C. SI unit of time is second. Therefore, the SI unit of current is Coulomb by second. It is also known as ampere. Then the next topic is current density. You like to see what is mean for current density. Current density is defined as the ratio of the current to the surface area whose plane is normal to the direction of charge motion. It is denoted by capital J and is a vector having direction of charge motion. So J equal to di by ds, or di equal to j dot ds, or we can write this equation J equal to I by A, we can write. Okay, the next topic is conduction current density, which is represented by the symbol J1. Current density, we have two types. The first one is conduction current density and a displacement current density. First, we would like to talk about conduction current density, which is represented by the symbol is J1. Let's see what is mean for conduction current density. The current density due to the conduction electron in a conductor is known as conduction current density. Oh, now we would like to derive the equation of conduction current density. By Ohm's law, the potential difference across a conductor having resistance R and current I is V equal to I R. Equation number 1. For a length L and the potential difference V, we can write V equal to E into, so equation number 2, where E is electric field intensity. Now from equation 1 and 2, we can write I R equal to E into F. Equation number 3. We know that the resistance R is directly proportional to length of the conductor and inversely proportional to area. So we can write this equation R directly proportional to L by A, or we can write this equation R equal to rho into L by A. We know that the value of rho equal to how much? 1 by sigma. So this equation becomes R equal to rho into L by A R is equal to rho L by A, which will be equal to 1 by sigma into L by A. by sigma into, so L by A is equation number 4. Next, where rho and sigma are the electrical resistivity and conductivity respectively. Now, using equation 4 in 3, substitute equation 4 in equation 3. I into L divided by sigma into A will be equal to E L. Then we are in this equation. Once we are in this equation, I divided by sigma into A will be equal to E. We know that the value of I by A is called as what? Current density. So instead of I by A, we can write J. So then the final equation can be written as J1 will be equal to sigma into E. So this equation is called as what? Conduction current density equation. Okay. So here J1 may be referred to as conduction current density, which is directly proportional to the electric field intensity. So far we discussed about conduction current density. Okay, next we would like to discuss about displacement current density. Let us see what is mean for displacement current density. There is no direct current in a circuit containing capacitor, while an alternating current can flow in it. The conduction current due to the motion of electrons cannot pass through a capacitor as its plates are separated by a dielectric material. As the current does not pass through the capacitor, so we have to conclude that in a capacitor, a certain process closes the conduction current, that is, it enables in some way a charge exchange between the capacitor plates without actually transporting a charge between the plates. So the current associated with this process is called as displacement current. The displacement current per unit area is known as displacement current density. Now we would like to derive the equation of displacement current density. The capacitor, the current is given by I equal to D divided by dt. We know that the value of Q equal to how much? C into V. So this equation becomes D into C V divided by dt. Equation can be rearranged. I will be equal to C dot dV divided by dt. This is equation number 1. Next, you would like to write the value of C. C is equal to how much? Epsilon A by D. In the equation number 1, Q, C and V represents charge across the plates, capacity and potential difference across the plates of the capacitor. In a pair plate capacitor, the capacitance is given by C is equal to epsilon A Next, where epsilon A and D represents electric permittivity, area of the plates of the dielectric filled capacitor, and distance between the plates of the capacitor respectively. Now, we would like to substitute equation number 2 in equation number 1. Using equation 2 in 1, I equal to epsilon A divided by D dot dV divided by dt, or like this equation I by A equal to epsilon divided by D dot dV by dt. Okay, we know the value of I by A. I by A is nothing but what? Current density. So instead of I by A, we can write J. In order to differentiate the previous case, now I by A will be represented as J2, and we would like to rearrange this equation. Okay, so we like to rearrange this equation. Now, instead of I by A, I would like to write J2, which will be equal to epsilon into